Today we're diving into the fascinating world of gradient descent, cornerstone technique in optimization and machine learning. Whether you're a student, a data enthusiast, or just curious about how computers learn, understanding gradient descent is essential. In this video, we'll break down the concept, explore how it works, and see why it's so widely used. We'll start with the basics, gradually building up to more complex ideas, ensuring you gain a solid grasp of the topic. Let's begin our journey by understanding what optimization means and why gradient descent is such a powerful tool in this field. Optimization is the process of finding the best solution from all possible options. In mathematics and computer science, it often means minimizing or maximizing a function. For example, you might want to minimize the error in a prediction model or maximize profit in a business scenario. Optimization is everywhere from engineering to economics, and it's the foundation of many algorithms. Gradient descent is one of the most popular methods used to solve these optimization problems, especially when dealing with complex functions that are hard to solve analytically. At the heart of optimization lies the concept of a function. A function takes an input, performs some operations, and produces an output. In machine learning, functions often represent the relationship between input data and predictions. The goal is to adjust the parameters of the function so that the output is as close as possible to the desired result. This is where gradient descent comes in, helping us tweak those parameters efficiently. Gradient is simply a vector of partial derivatives. It points in the direction of the steepest increase of a function. In optimization, we're usually interested in minimizing a function, so we move in the opposite direction of the gradient. Think of it like hiking down a hill. The gradient tells you which way is uphill, so you go the other way to reach the bottom. Imagine a three-dimensional landscape with hills and valleys. The function we want to optimize is like this landscape, and our goal is to find the lowest point, the minimum. The gradient at any point tells us which direction is steepest uphill, so by moving in the opposite direction we can descend toward the minimum. This visualization helps make sense of how gradient descent works in practice. Gradient descent is an iterative algorithm. It starts with an initial guess for the parameters, then repeatedly updates them by moving in the direction opposite to the gradient. With each step, the parameters get closer to the optimal values that minimize the function. This process continues until the changes become very small, indicating that we've reached a minimum or are very close to it. The core formula for gradient descent is simple yet powerful. New parameter equals old parameter learning rate gradient. Here, the learning rate controls how big each step is and the gradient tells us the direction. By applying this update rule repeatedly, we can gradually approach the minimum of the function. Learning rate is a crucial parameter in gradient descent. If it's too large, the algorithm might overshoot the minimum and fail to converge. If it's too small, the process becomes very slow. Finding the right balance is key to efficient optimization. Often, practitioners experiment with different learning rates to see what works best for their specific problem. Convergence in gradient descent means that the algorithm has reached a point where further updates make little or no difference. This usually happens when the gradient becomes very small, indicating that we're near a minimum. Monitoring convergence is important to avoid unnecessary computations and to ensure the algorithm doesn't get stuck in an endless loop. There are several variations of gradient descent, each with its own strengths and weaknesses. The three main types are batch gradient descent, stochastic gradient descent, and mini-batch gradient descent. Each type handles data differently, affecting speed and accuracy. Let's take a closer look at each one. Batch gradient descent computes the gradient using the entire dataset for each update. This approach is stable and produces accurate results, but it can be slow and memory-intensive for large datasets. It's best suited for smaller datasets where computational resources are not a major concern. Stochastic gradient descent, or SGD, updates the parameters using only one data point at a time. This makes it much faster and more scalable for large datasets, but it introduces more noise into the updates. The randomness can help escape local minima, but it may also cause the algorithm to bounce around the minimum. Mini-batch gradient descent strikes a balance between batch and stochastic methods. It updates the parameters using small, randomly selected subsets of the data. This approach combines the efficiency of SGD with the stability of batch gradient descent, making it the most popular choice in practice. Gradient descent is widely used in machine learning to train models. It helps find the best parameters that minimize the loss function, which measures how well the model predicts the data. From linear regression to deep neural networks, gradient descent is the engine that drives learning. A loss function quantifies how far off a model's predictions are from the actual values. The goal of training is to minimize this loss. Gradient descent works by calculating the gradient of the loss function with respect to the model parameters and updating them to reduce the loss. Let's consider linear regression, a simple yet powerful machine learning algorithm. The goal is to find the line that best fits the data points. Gradient descent is used to adjust the slope and intercept of the line so that the sum of squared errors between the predicted and actual values is minimized. Neural networks, gradient descent is used to update the weights and biases of each neuron. The process is similar to linear regression but involves many more parameters and layers. Backpropagation, a key algorithm in neural networks, relies on gradient descent to efficiently compute the gradients for all parameters. Backpropagation is the process of calculating the gradients of the loss function with respect to each parameter in a neural network. It works by applying the chain rule of calculus, allowing efficient computation of gradients even in deep networks. Gradient descent then uses these gradients to update the parameters and improve the model. One challenge in gradient descent is the presence of local minima, points where the function is lower than nearby points but not the lowest overall. The algorithm can get stuck in these spots, preventing it from finding the global minimum. Techniques like using momentum or random restarts can help overcome this issue. Besides local minima, gradient descent can also struggle with saddle points and flat plateaus. At a saddle point, the gradient is zero, but it's not a minimum. Plateaus are regions where the gradient is very small, causing slow progress. Advanced optimization techniques can help navigate these tricky areas. Momentum is a technique that helps gradient descent move faster and avoid getting stuck. It works by adding a fraction of the previous update to the current one, smoothing out the path and helping the algorithm overcome small obstacles. This can lead to faster convergence and better results. A learning rate schedule adjusts the learning rate during training. For example, it might start high and gradually decrease as the algorithm approaches the minimum. This helps ensure fast progress early on and fine-tuning as we get closer to the optimal solution. Beyond basic gradient descent, there are adaptive methods like AdaGrad, RMSprop, and Atom. These algorithms automatically adjust the learning rate for each parameter, making optimization more efficient and robust. They're widely used in deep learning for their ability to handle complex, high-dimensional problems. Real-world applications, gradient descent is used in everything from image recognition to natural language processing. It's the backbone of many state-of-the-art models, enabling them to learn from data and make accurate predictions. Understanding how to implement and tune gradient descent is a valuable skill for anyone working in data science or AI. Despite its power, gradient descent isn't foolproof. Common pitfalls include choosing a poor learning rate, getting stuck in local minima, or failing to preprocess data properly. Being aware of these challenges and knowing how to address them is key to successful optimization. Feature scaling is an important preprocessing step for gradient descent. When features have very different scales, the algorithm can struggle to find the optimal path. Scaling features to a similar range ensures that gradient descent works efficiently and converges faster. How you initialize the parameters can affect the performance of gradient descent. Good initialization can lead to faster convergence and better solutions, while poor choices might slow down learning or cause the algorithm to get stuck. Common strategies include random initialization and using heuristics based on the problem. In some cases, gradients can become very large, causing unstable updates. Gradient clipping is a technique that limits the size of the gradients, preventing them from exploding. This is especially useful in training deep neural networks where large gradients can disrupt learning. Regularization is used to prevent overfitting in machine learning models. Techniques like L1 and L2 regularization add a penalty to the loss function, encouraging simpler models. Gradient descent incorporates these penalties during optimization, helping models generalize better to new data. Early stopping is a practical technique to prevent overfitting. By monitoring the performance on a validation set, we can stop training when the model starts to perform worse, even if the loss on the training set continues to decrease. This ensures the model doesn't memorize the training data at the expense of generalization. While gradient descent is powerful, it's not the only optimization method. Alternatives like Newton's method or genetic algorithms have their own advantages and use cases. Gradient descent is preferred for its simplicity and scalability, especially in high-dimensional problems. Gradient descent has a rich history with roots in calculus and mathematical optimization. It has evolved over decades, becoming a fundamental tool in modern machine learning and artificial intelligence. Understanding its origins helps appreciate its impact and continued relevance. From self-driving cars to voice assistants, gradient descent powers many technologies we use every day. Its ability to optimize complex models makes it indispensable in fields like healthcare, finance, and robotics. The next time you use a smart device, remember that gradient descent is working behind the scenes. Visualizing the optimization process can provide valuable insights. Tools like TensorBoard allow you to track the loss and gradients during training, helping diagnose issues and improve performance. Visualization makes abstract concepts more concrete and accessible. Deep learning relies heavily on gradient descent to train large, complex models. With millions of parameters, efficient optimization is crucial. Techniques like mini-batch gradient descent and adaptive optimizers have made it possible to train deep networks on massive datasets. As datasets grow, training models with gradient descent can take a long time. Parallel and distributed training techniques allow computations to be split across multiple processors or machines, speeding up the process. This is essential for handling today's big data challenges. Choosing the right hyperparameters like learning rate and batch size is critical for successful gradient descent. Hyperparameter tuning involves experimenting with different values to find the combination that yields the best results. Automated tools can help streamline this process. Monitoring the optimization process is vital for catching problems early. By tracking metrics like loss, accuracy, and gradients, you can identify issues such as vanishing or exploding gradients. Debugging tools and careful observation help ensure smooth training. Vanishing and exploding gradients are common issues in deep networks. When gradients become too small, learning slows down or stops. When they become too large, updates become unstable. Techniques like normalization and gradient clipping help address these problems. To get the most out of gradient descent, start with a simple model and gradually increase complexity. Use visualization tools to monitor progress and don't hesitate to experiment with different settings. Remember, successful optimization often requires patience and persistence. Let's look at a real-world case: image classification. Here, gradient descent is used to train a neural network to recognize objects in photos. By minimizing the loss function, the model learns to distinguish between different categories, achieving impressive accuracy on unseen images. In finance, gradient descent is used to train models that predict stock prices. By optimizing the parameters, the model can identify patterns in historical data and make informed predictions. This application demonstrates the versatility of gradient descent across industries. The field of optimization is constantly evolving. Researchers are developing new algorithms and techniques to make gradient descent even more efficient and robust. As machine learning models grow in complexity, the importance of effective optimization will only increase. To wrap up, gradient descent is a powerful and versatile optimization technique. It's the engine behind many machine learning models, enabling them to learn from data and make accurate predictions. By understanding its principles, variations, and practical tips, you're well equipped to apply gradient descent in your own projects. Thank you for joining this deep dive into gradient descent. We hope you now have a clearer understanding of how it works and why it's so important in optimization and machine learning. Keep exploring, keep learning, and remember, optimization is a journey, not just a destination.